Now we're on to section 6.4 and we're looking for projectile motion formulae. Now what's interesting here is that actually we could use the techniques that we've got to answer any question that we want to about a projectile. So if I tell you that a projectile starts off with a certain velocity at a certain angle, then we know it's going to move like this and it's going to hit the ground somewhere over here. We could ask for, what could we ask for? We could ask for the time it takes to do that. We could ask for the time it takes to get to the top. We could ask for the speed it hits the ground with. Oh, well, never mind, the speed it hits the ground with is going to be the same as the speed it starts off with, isn't it? But we could ask for the speed at different points. We could ask for, well, various different things that we've already seen. Now, if we just do that without labeling any of these things, we don't put any numbers in, then maybe we can get some formulae which we could just follow through and save ourselves a little bit of time. And that's what we're doing in this section. So if you flip over to page 122, then we find there is an equation for the time of flight. So how long does it take? Well, if I just do the same equations as before, but leave letters in instead of putting any numbers in, then I'll find an equation for the time of flight, and it turns out to be this thing, and we'll see that in a second. The time it takes to reach the greatest height, well, that unexpectedly is half of the time of flight, isn't it? So we're not too surprised about that one. We could ask for the horizontal range, that is this distance here, and we can work that one out from these three bits of information. And if we do that without putting any numbers in, it turns out to be this. So we can get those three formulae. Now, the new one is this, equation of trajectory. And what that is it will tell you how far it's moved horizontally and link that to how far it's moved vertically. So if you tell me how far we've gone horizontally, I'll tell you the height of the object. Now again, we could find that before, but that equation of trajectory is a neater way of doing it. Now what you'll find is that from these four formulas, sometimes you'll have a choice. You can do it with the methods from section 6.1, 2 and 3, and sometimes you'll want to do it with the method from section 6.4. Sometimes they won't give you a choice and they'll specifically ask you to do one method over another. The one that's particularly useful is this equation of trajectory, because that's for questions like, when we've gone this many meters horizontally, what's the height of the object? A typical question like that might be, you're throwing a ball, there's a wall, right? You know, and you're throwing a ball from here with a certain velocity. Is the ball going to hit the wall? Is it going to go over the wall? So you can say, well, okay, if the wall is 10 meters away, then with this initial velocity, when I've traveled 10 meters horizontally, what's the height vertically? If the wall is 3 meters high, then if the vertical height is more than 3 meters, then I'm going to go over the wall. If the vertical height is less than 3 meters, then the ball's going to hit the wall. So to do that, it helps to have y, the vertical displacement, linked in an equation to x, the horizontal displacement. You put 10 in for x, and you can work out the y. Okay, so that's how the equation is going to be useful. So let's go through now and look at the derivation. Now the derivation is in the blue boxes on page 120 and 121. So the only reason to keep watching this video is if you have looked through those blue boxes and you're not quite sure where they're getting these equations from, and I'll talk you through that now. It doesn't particularly matter if you find it a bit confusing at first, because we're basically going to use these formulae, but you should be able to generate these formulae for yourself anyway, because all we're doing is the same techniques as before, but we're just not putting any numbers in. We're just dealing with letters purely. So what do? We go at an angle of alpha and an initial velocity of u. So I'm going to try and keep to the same notation as the book. Horizontally, I get s equals vt. So s, the horizontal displacement by the time we hit the ground. Now we're calling that r, equals the horizontal component of this, which is u cos alpha times by t. Okay, u cos alpha times by t. Vertically, we have u, v, a, s, and t. A is gravity pulling downwards, and we're going to put that in as minus g. Displacement, when I hit the ground again, vertical displacement is 0. Initial velocity is u sine alpha, and the time it's taken is the same as this time it's taken here, and I'm going to ignore the speed with which it hits the ground. So that's all the information. We're going to need here s equals ut plus 1/2 at squared, and then let's just start putting things in. So s equals 0, u sine alpha times t minus g over 2, that's minus a half, that's plus a half a, is minus g over 2 because g is negative, times t squared. So 0 displacement when? Well, let's factorise out the t. When t equals 0, well, of course, the 0 displacement when t equals 0, because when we started the clock, we're sitting on the ground. And the other 0 displacement is when this equals 0. So u sine alpha minus g over 2 equals 0. In other words, g over 2 times t. In other words, 2u sine alpha over g equals t, which you can see by taking this onto the other side, times by the 2 divided by the g. So the time it takes to move all the way up and all the way down is t. We could, if we want, repeat that experiment and put v, the final velocity, as 0, and that would spit out that the time taken is u sine alpha over g, or we could just use the fact that we know from last year that vertically it's going to be a symmetrical motion. It takes the same amount of time going up and the same amount of time going down, and that will give us the time it takes to get to the top as u sine alpha over g. So there's two of our formulae from page 122. If I take this t here and I substitute that in to this equation 1, so if I substitute equation 2 into equation 1, then I'm going to get r equals u cos alpha times by t, which is 2 u times u is u squared, cos alpha sine alpha over g. So there is, from here, the time of flight for the whole thing is 2u sine alpha over g. Take the 2 off, we get u sine alpha over g is the time it takes for half the flight, i.e. to get to the top. And r equals this thing. So we are 3/4 of the way there. Oh, sorry. 2 cos alpha sine alpha is sine 2 alpha. So finally we're there, which is the first 3 of our formulas there. If you haven't seen that 2 cos alpha sine alpha, it's in the pure blue book, second year, and I think it's chapter 7. So if you haven't covered that in lessons yet, then you can maybe go and look at the video on my playlist and just see that one being proved true. Section 7.2 or 7.3, something like that. So that leaves us just with the equation of trajectory to work out. And that's going to be, I'm going to set off with the same setup, u and alpha, but I'm not now looking at what the displacement being 0, at the final bit. I'm just looking at getting to this point here, a horizontal distance of x and a vertical distance of y. Okay, so on an x and y axis. So how long does it take to get to there? Well, horizontally, s equals vt. So the displacement horizontally is x. Velocity horizontally is u cos alpha, and t, time taken, is t. So horizontally, to get to some point chosen at random on this curve, we've got that. Vertically, u, v, a, s, and t. The initial vertical velocity is u sine alpha. The vertical velocity at this point I don't know. The acceleration is minus g. The vertical displacement is y, and the time taken is t. So s equals ut plus 1/2 at squared. S is y. Our initial velocity is u sine alpha, where that u is now this u. U sine alpha times t minus g over 2 times t squared. Now if I take this equation here, I can see that t is x over u cos alpha. There's equation 1, there's equation 2, and if I substitute from equation 1 into equation 2, can you see, let's just try and sort of see through the symbols for a minute. This equation has just got an x and a t there. This one has got a y and a t. So if I get rid of the t, I'm going to have y in terms of x, and what else is going to be in there? Well, u and alpha and g. So if I know G, which I do as long as we're staying on Earth, and I know U and alpha, then I get Y in terms of X, which is what we wanted, right? So Y equals U sine alpha times T, which is X over U cos alpha, so the U's are going to cancel there, minus G over 2 times T squared, which is X squared over U squared cos squared alpha. Now, we have actually done the job there, but let's just tidy it up a little bit. Sine over cos is tan alpha. And let's just make sure we get this in the same form as the textbook. Let's see, minus G over 2 X squared over U squared cos squared alpha. And to get this into its standard form, I'm going to rewrite it in this way. I've got G over 2 X squared over U squared, and then we've got 1 over cos squared. Well, 1 over cos squared, if we just take a look at the side for a minute, is sec squared. And again, this is the second year blue book, trigonometry chapter 7. So, oh, this might be chapter 6 actually. So sec squared, and sec squared can also be written as 1 plus tan squared. Okay, so my equation here turns into Y equals tan alpha x minus, and again I'll just check the book and write it in the same way that they do, G x squared 1 plus tan squared alpha over 2u squared. And there's my x in terms of y. Now let's have a look at that again, because it's a nasty looking equation, but can you see that tan alpha, that's just a number, right? G and 1 plus tan squared alpha over 2u. Well, if I know what alpha and u are, then that bit in red is just a number, this bit in red is just a number, this bit in red is just a number. So this is y equals something times x minus something or other times x squared. So what we've found there is that y in terms of x is a quadratic equation, isn't it? And it's a quadratic equation with a negative coefficient of x squared. In other words, it's a parabola, and it's a parabola which is this shape. And if you look at it, that's what we've always been drawing all the way through the chapter. These projectile motions are always parabolas. The other thing we know about parabolas is that they are symmetrical. So these motions are symmetrical, and again, we've been making that assumption all the way through the chapter. We know the motion is symmetrical because the time it takes to get up is the time it takes to get down, and therefore the distance, horizontal distance to the maximum point is the same as the horizontal distance to the point where it hits the ground again. So, all equations proved, and mixed exercise 6 awaits you. Enjoy that one, hope it goes okay.